Hello, everyone. Thanks for tuning in to our last episode of this summer series live session on LinkedIn and YouTube. I'm Jun Lee from AVL, Senior Technical Sales Specialist at AVL Advanced Simulation Technologies. So AVL, if you don't know us, is one of the world's leading mobility technology companies for development, simulation, and testing in the automotive industry, and also in other sectors such as energy, aerospace, and marine. Today, I'm joined by Diogo Lopes from 52, the team behind PreonLab. Together, we're going to talk about simulating some unconventional fluid. When I say unconventional fluid, I don't just mean exotic laboratory material. In fact, you have met them at your dinner table, like the ketchup that won't leave the bottle or the toothpaste that stand up on your brush. So those are all unconventional fluids. Those are the material that don't always behave like water or air. But with modern CFD tools like PreonLab, we can actually model them and get useful insight for real-world engineering. Now, I will pass it to Diogo to introduce himself and 52 and dive right in.
So, hello everyone, my name is Diogo and I'm an application engineer at 52 Technology. And 52 Technology is a software company and we are based in Germany, in Freiburg in Breisgau. And our main product is PreonLab, which is a CFD tool, which we'll present and talk about today. So let's jump into the next slide and talk a bit about the technology fundamentals behind PreonLab. And PreonLab uses the smoothed particle hydrodynamics method. It's called, the short is SPH. And below we have two different reference frames that are used in the traditional CFD codes. And in the right, we can see the Euler reference frame where the fluid domain is discretized into a mesh. And we can see a mesh here. And for example, in the finite volume method, these small parts of the mesh are called cells. And then what's done, we apply the governing equations of fluid flow, which are mass and momentum conservation to each cell. And then we ensure that we get a conservation inside this cell. And in this way, we compute the variables that we want. So in the case of fluid dynamics, of course, we're talking about pressure and velocity. And this method is really efficient to compute the spatial derivatives. However, for some flows like free surface flows where there is a large deformation of the fluid, and for example, in the case of gearbox where we have oil and air, and this interface between oil and air is constantly changing, it's quite difficult to get a mesh that fits this flow. So for that, we usually do not use these Euler reference frame methods, and we use something like PreonLab, which is based with a Lagrangian frame of reference, where basically our fluid domain is not discretized into a mesh. So in PreonLab, we have no mesh. The fluid is rather discretized into particles, and these particles are carrying the physical quantities of mass, pressure, and velocity. And then we apply the same governing equations of fluid flow, the mass and momentum conservation, to the particles themselves. And these particles are all interacting with their neighboring particles. And in SPH, we have something that we call the kernel functions, which govern basically the interaction between the particles and their neighbors. And as I said, because we have no mesh and we have this slightly different mathematical scheme behind PreonLab, this tool is really, really efficient for free surface flows whenever we have these large fluid deformations and these interfaces between different phases changing a lot. So now that I presented the mathematics behind PreonLab, and if you are curious about it, you can also check our website at 52.eu to get more information about our product. Next, I will talk a bit about the development principles behind PreonLab. And whenever we are developing this product, we are focusing 3 pillars. And The first is usability. Our tool is intended to be the most user-friendly possible. And for that, for example, we have an all-in-one tool where we do the pre-processing, the simulation, and also the post-processing when getting the results. It's all done in one tool and the same graphical user interface. We did it all just in one window. I previously used some CFD tools where we had, for example, the geometry done in one program, then you close this program, then you open, for example, to do the mesh, then you close, then you do the simulation. So PreonLab does it all in one, which is a great advantage and makes the workflow really lean. And of course, as I mentioned before, because of the theory behind SPH and also PreonLab, we don't use any meshing. So basically, you don't need to spend a lot of time meshing a complex geometry. So what we do is basically import the geometries, put some boundary conditions by some volume sources or area sources rather, and then just simulate and get the post-processing of the results. And also we have also in PreonLab a really powerful render that will create some great images, which we will see next in our presentation. Second pillar of PreonLab is efficiency. Of course, in every simulation and every simulation tool, what we want is to produce results as fast as possible, because we use these tools in the cycle of development of products, and we want to do some testing of some phenomena in real life and simulate it, and we want to save time to our customers. So for that, we look to make PreonLab really fast, and we offer the computation in both CPU and GPU structures, and also in parallelized computation in MPI and multi-GPU. And one tool and one feature that really distinguishes PreonLab in comparison to the competitors in our SPH field is the continuous particle spacing, which the short is CPS. And basically CPS stands for particle refinement, and we can get a simulation with different particle sizes. And for example, in a case of an internal flow, I can use a smaller particle size close to the boundary where the velocity gradients will be bigger. And in this case, I can save a lot of time in our simulation. And this is something similar to a mesh refinement in the traditional CFD tools. And the final pillar, and one of the most important, of course, we want to make it PreonLab easy to use and produce fast results, but these results need to be trusted. And for example, whenever we are developing a new feature in PreonLab, we run it through a lot of different benchmarks. This can be experimental data from our customers and also from reference papers in the literature. And right now, PreonLab is used by more than 100 companies in all 5 continents. So we can say that we are trusted by a lot of different entities, and this makes us, of course, very proud. And yeah, these are the 3 pillars of development behind our product. And now we're gonna do a small introduction to our topic today, which is unconventional fluids. As June mentioned in the beginning, there is not only the flow of water, which is quite simple. Water is a Newtonian fluid, which that means that it obeys to the Newtonian law of viscosity. So whenever I put a force, for example, in water, I expect a deformation. And if I put 3 times more force, I will get 3 times the amount of deformation rate. So in the case of water, this is linearly proportionate, and it's called viscosity. We have the light blue curve in this graph. But for example, we have different fluids like ketchup, as June mentioned. And in the case of ketchup, is a shear thinning fluid, which means that the more we agitate ketchup, the easier it flows. And this is one of the non-Newtonian fluids that we may be showcasing today in our later demonstrations. And you can model all of these fluids in PreonLab. And for that, we have 2 different distinct viscosity models. The first one is the Herschel-Bulkley model. And this one is quite useful because it allows us to model also the fluids which need a yield stress, an initial yield stress to flow. So for example, in the case of toothpaste, whenever the toothpaste is in the recipient and you agitate it a little bit, it doesn't flow. So it needs an initial stress in order for it to flow. And then the more that you press the toothpaste, the easier it flows. So this toothpaste behavior can be modeled with the Herschel-Bulkley model in PreonLab. And this viscosity model also allows us to model just the simple shear thinning and shear thickening fluids without the initial yield stress when this parameter on the equation is 0. And we also offer another viscosity model, which is named the Carrier-Yasuda. And for this one, we don't have the option of using the initial yield stress, but the mathematics behind this equation allows us to model different transitions between the different viscosity at high and low shear height. And with these two viscosity models, we can basically simulate all types of different viscosity models and all types of fluids. And that's what we're gonna show now. And June, I give it back to you.
Thanks, Diogo. So the first use case we are seeing here is the hot melt adhesive spreading. So this is an application in the window and the door industry. So here you can see this is a window frame with a corner key inside. So we inject this adhesive at a relatively high temperature adhesive into the hole of this this frame, and then it will bond this corner key with the window frame together. So at 170 degrees C, the adhesive behaves more like a Newtonian fluid for this one. So so we learned from our customer that in the past, they had to build the prototype parts and physically test it. So this typically take a week, 1 week per design iteration. So right now, with the PreonLab, they can simulate the adhesive flow in such a setting in just a few hours. So this means like you don't only save the time, you also get better insight. For example, on the right, like where the adhesive might pool and where you risk like dry spot, so that you can quickly improve the design, and even before you change the hardware. So let's move to the next use case.
Yeah, the next use case that we have here is a battery model assembly. And in this case, basically what we have is a battery that is charging. And of course, during the charging process, there is some heat generation and the temperature inside the battery goes up. And of course, here we want to simulate the cooling down of this battery. And we use a gap filler or a thermal paste that we call it here to help improve the heat conduction between the battery and the cooling plate, which is in green at the bottom. And in the case of this simulation, we used a Carrier-Yasuda model to model the viscosity of the fluid. And what the insights that we want to get in this simulation is basically the distribution of the thermal paste on the model. We want to assure that all the battery is in contact with the paste and therefore in contact with the cooling plate, maximizing the heat transfer. And we want to also get insights on the loads on both the module and the cooling plate to see whether, for example, there are some components in the battery that can stand these loads. And of course, we also want to ensure that there are no air pockets in the paste, so that of course, with air, the heat transfer will be less. So we go to the next slide. And we see here the study that we did was to inspect the different initial depositions of our gap filler, of our thermal paste, and with the pressing of the battery, we want to infer on the different geometries at the end of the simulation and get in this way to know, okay, which is the better geometry that can provide the highest heat transfer for my setup. So in this case, we had 4 different initial geometries. We call it long stripes, short stripes, the cross, and also a big blob. And with this simulation, we got the final geometry, the final fluid geometry. We got to export this one via the Preon Mesher, which is a tool that we have in PreonLab that allows us to export our fluid to an STL or OBJ file. And then we imported this STL file to IVL file, where the thermal analysis were done. So basically here, we wanted to know which initial deposition of the gap filler is better to improve the heat transfer between the battery and the cooling plate, minimizing in this way the heating process in the battery. So that's one of the other insights that we can get. And in this case, we use the Carrillo-Yasuda viscosity model.
So let's move on to something quite different, the dust. So on the moon surface, there is a very thick layer of this dust layer. We call it lunar redness. So this dust are some kind of, including the fine particles, also broken rocks, and etc. etc. Most of the time, this is very sharp and abrasive. So when you are designing a lunar vehicle, let's say, you're going to consider like this dust behavior, because it not only affects its mobility of your vehicle, the visibility, and also it will affect the lifespan of the component because of this abrasive dust. So the challenge is to understand where the dust goes. So then we can test the strategy to mitigate this the challenge. So with PreonLab, we can capture those dynamics virtually, which will help the engineers explore the solution that would be extremely costly and time-consuming to test in the real life. So there are several advantages for the PreonLab in these scenarios. So first of all, as Diogo mentioned, this is a meshless approach, so which allows us to quickly evaluate different designs. We don't have to generate any mesh. And then secondly, we can allow the realistic terrains, for example, the moon surface terrain, to be scripted and into this into a surface, and then we can use that real terrain as our surface for this vehicle to move on. And then last but not least, we can simulate dust, as I'm going to show you in the next slides here. So the dust property need to be calibrated so that we can model the dust in a more realistic way. Here we use this reckless angle of the repose data from experiment work at UCF. So by tuning the particle size and the solver properties, solver parameters against that reference, we can get pretty accurate behavior without like massive full vehicle simulation every time. So as you can see on the right side, so we did quite a good validation of our the dust behavior. Now let's move on to,
Yeah, next application is slightly different from the dust in the moon. So here we have blood flow, and for the case of blood flow, this was done, this study of the blood pump was done when I was trying to validate the implementation of the Carrillo-Yasuda model. So the Carrillo-Yasuda model is the one that was chosen here, and we can see the curve in the image above with the blood pump. That's the viscosity of blood against the shear height. And in the case of this, whenever we are simulating a blood pump, we want to ensure that the blood pump is working properly. and that means that it's providing a constant blood flow supply to the outlet. And as engineers, we can also get insights into the forces and the stresses that are in the impeller, which is the main component of this pump. And when designing something like this, we want to, of course, avoid the regions where the velocity is low and there's also a lot of recirculation, because these areas are prone to develop clotting or clots. And of course, this is not wanted because we want to minimize the appearance of this in the blood, right? And the simulation below is more of a demonstrative simulation that we did to showcase the linear elastic solver. And in this case, there is this movement of the blood bag is used to mixture the blood with the anticoagulant to avoid that the coagulation of blood. And in this simulation, we wanted to showcase basically the behavior of the bag. And in a simulation like this, you can get insights into the forces and the stresses on the bag and possibly look out for rupture or leakage of some points. And as I mentioned, again, the Carrier by Suda was the proper model to simulate blood flow.
So here is another adhesive application. So this is in the manufacturing process. Sometimes it's quite challenging because you want a uniform layer of this glue on the surface. You don't want any bubble, and you don't want any gaps, and you want a consistent thickness. So this is quite challenging sometimes. With PreonLab, we can simulate this how this glue behaves on the surface and help the engineer virtually to optimize the application process, making sure the right amount of glue goes to the right place. So saving both the cost and then the rework. Here's another tricky one, the foam encapsulation for the battery pack. So the foam encapsulation can add structured stability to the battery pack, and by holding the cells in place to protect them from the shocks or vibration, it can also absorb the combustion particles in case of thermal runaway events. So in this manufacturing process, we need to manage the nozzle location and how many nozzle we want to put in, and then what's the injection time, and so on. So because also this foam expands and its viscosity change with time. So predicting its behavior is really complicated. PreonLab allow us to simulate this lifetime dependent material behavior and get a clear picture of how this foam will fill the pack before we really design the hardware. So, but I have to mention that we don't simulate the chemical reactions in this process at the moment. So.
Yeah, next application is more of an automotive industry application. And here we are showcasing a simulation of mud, which is air shell Buckley fluid, which means that there is an initial yield stress that needs to be overcome in order for the fluid to flow. And here we are comparing two different designs, and the one below includes an elastic mud flap. And this simulation basically showcases, again, the linear elastic solver in conjunction with the fluid solver. And the goal of this simulation was, of course, to inspect the deposition and wetting patterns on the sidewalls of this truck. And we can clearly see that with the mud flap in the bottom, the amount of mud that goes to the side door, it's much lower whenever we have a mud flap. And of course, with this simulation, we can also get insights into the stresses, and them can give us, of course, useful information to optimize the geometry and also the mounting points of the mud flap. Next one is something similar to mud. It's called marsh, which is slightly different fluid, probably a bit more vegetation included in the fluid. And this is a wading simulation. Here we have a truck that goes to this pool of marsh. And the goal in a wading simulation is to evaluate the hydrodynamic forces on the components of the car, usually the underbody panels, some elements of the suspension. And also we want to get insights into the wetting and deposition and the adhesion of the marsh to the truck. And we want to see if there is some some marsh goes to some unintended parts of the car. So the ingress of marsh to the components of the car is also some insight that we want to check in this simulation. And as we saw here, we also want to see whether the cleaning of this marsh is possible with some jet, for example, jet of water. So again, marsh is a similar fluid to mud, so we also use the Herschel Buckley because of this initial yield strength. And that's one other application for the automotive industry.
So lubrication is a classic application for PreonLab. So the challenge is to ensure the critical area is properly lubricated, and then also to minimize the churning loss and maintain efficiency. So with this simulation, you can explore different like oil volume and different component layout, and immediately see how the oil distributes inside of the system. So this will then reduce the reliance on the testing and then accelerate the optimization. In this simulation, we only need to load the surface. We don't need to generate, as comparing to the traditional CFD, we don't have to generate any like sliding mesh or any mesh like that. So this saves significant time. The traditional mesh CFD typically has to generate the mesh in like several days or even weeks for this kind of simulation. And then PreonLab just take a couple hours, load the surface mesh and set it up. And then you can initialize the oil volume and then start the simulation. So it's quite time saving comparing to the traditional CFD.
Final showcase that we are showing today is the dishwasher. And in this case, we have the non-Newtonian fluid, which are the pumpkin soup and the ketchup that are leftovers in the plates. And yes, with this simulation, we wanted to get insights into the design of the nozzle on the arm. So basically, we wanted to maximize the exposure of water to the plates and also maximize the shear stress on the plates so that this dust of ketchup could be removed from the plates. And here, some parameters that we studied were the nozzle, the location, the number, also the orientation, and also some diameters. Everything that we wanted to get insights here, we could do it in PreonLab. And for this simulation, for example, I want to highlight the powerful rendering tool that we have, and this is also included in PreonLab that can get us like images like this, where we can clearly see what's happening inside the dishwasher, and we can get some really high quality images that allows us to make these nice videos. So, June, I get it back to you.
All right. So to wrap this up, so what really set PreonLab apart is the meshless approach. It's fast to set up and give instant visual feedback and keeps the workflow clean and lean and clean. So you can see on this animation, PreonLab not only have this powerful rendering, it also captures the physics correctly. So you can see with the small droplets on the wind, the rain droplets on the wind panel, the small droplets will stay there, and as it grows bigger, it starts to flow down. Its gravity overcomes the surface tension, and so we have a good adhesion model. We call the lateral adhesion model to deal with this dynamic contact angle of this water liquid here. So that's a wrap up for today's session. So big thanks to Diogo from 52 for sharing his insight, and thanks to all of you for hanging out with us. We covered a lot from mud in the overall application to the dust in space to adhesive and oil in automotive and electronics, and then to biometric fluids like blood. So hopefully we got a sense of how PreonLab and the AVL can help you to tackle these unique challenges. If you got any questions, ideas, or just want to keep the conversation going, feel free to reach out to us here on the LinkedIn post or YouTube post. We'd love to hear from you. So thanks again for joining, and we will hopefully see you in the winter.